Have you ever felt a pull so strong you couldn't escape? A current, a memory, a feeling. The universe has its own version of that, an absolute point of no return. It is the ultimate prison, a place where space and time break down and the laws of reality are rewritten. It is called a black hole. And tonight, we are not just going to talk about it. We are going on a journey, a hypothetical voyage to the edge and over it. This is not just a science lesson. It is an exploration of the most extreme environment in the cosmos. We will travel to the event horizon, cross that silent threshold, and witness what physics predicts would be our final, terrifying, and awe-inspiring moments. So, secure your vessel, quiet your mind, and prepare to venture into the silent mystery. What really happens when you fall into a black hole? Before we can fall into a black hole, we must first understand how it fell into our minds. It wasn't discovered through a telescope. It was found in the ink of an equation. The story begins not in the darkness of space, but in the brilliant mind of Albert Einstein. In 1915, his theory of general relativity redrew our picture of the universe. Gravity, he proposed, was not a force pulling us down, but a curvature in the very fabric of spacetime itself. Massive objects, like stars and planets, warp this fabric, and that warping is what we feel as gravity. It was a revolutionary idea, and the mathematics were incredibly complex. Within just a year, a German physicist named Karl Schwarzschild, serving on the Russian front during World War I, found the first exact solution to Einstein's field equations. His calculations described the gravity of a single, spherical, non-rotating mass. But buried within his solution was something bizarre, something that even Einstein found unsettling. Schwarzschild's math showed that if you could compress enough mass into a small enough space, what we now call the Schwarzschild radius, the curvature of spacetime would become infinite. It would collapse in on itself, forming a point of infinite density, a singularity. Surrounding this point would be a boundary, a one-way door from which nothing, not even light, could escape. For decades, this idea remained a mathematical curiosity. Most physicists, including Einstein, believed such an object could never form in the real universe. They were called dark stars or frozen stars. The name that finally stuck, black hole, was coined much later in the 1960s and popularized by the physicist John Wheeler. It was then that our understanding began to accelerate. Astronomers realized that massive stars, far larger than our sun, could indeed collapse under their own gravity at the end of their lives, creating the very conditions Schwarzschild had described. The theory moved from the blackboard to the cosmos. And then came a giant of modern physics, Stephen Hawking. In the 1970s, Hawking stunned the scientific world by showing that black holes were not entirely black. Due to the strange rules of quantum mechanics near the event horizon, they should leak a faint glow of radiation, now known as Hawking radiation. This meant that over incomprehensibly long timescales, black holes could actually evaporate and disappear. From Einstein's elegant theory to Schwarzschild's wartime calculations, and from Wheeler's catchy name to Hawking's quantum revelation, the black hole has been a source of profound mystery and discovery. It is the ultimate laboratory for testing the limits of our knowledge. And now, armed with this history, our journey can truly begin. Imagine our vessel gliding through the silent vacuum of space. Before us, there is nothing, a patch of darkness that seems to swallow the starlight behind it. This is our target, a stellar mass black hole born from the collapse of a star 20 times the mass of our sun. From a safe distance, it is deceptively peaceful. Its gravity is no different from any other object of the same mass. If we replaced our sun with a black hole of the same mass, Earth would continue to orbit it just as it does now. We would freeze in the darkness, but we would not be instantly sucked in. The danger of a black hole isn't its pull from afar, it's its compactness. It is all that mass squeezed into an impossibly small point. As we move closer, strange things begin to happen to the light around it. The starlight from behind the black hole appears distorted, warped. This is gravitational lensing. The black hole's immense gravity is bending the path of light, creating a halo of smeared, twisted starlight around the central darkness. It's like looking through the base of a cosmic wine glass. Our onboard computer warns us of the tidal forces. Even out here, the gravitational pull on the front of our ship is slightly stronger than the pull on the back. For now, the difference is negligible, but it's a chilling preview of what's to come. And then we see it, or rather, we see its boundary, a perfect sphere of pure blackness. This is the event horizon. It is not a physical surface. You could pass through it without feeling a thing. It is a mathematical boundary, the point in space-time where the gravitational pull becomes so strong that the escape velocity exceeds the speed of light. This is the point of no return. Any signal we send out from beyond this line can never reach the outside universe. Any course correction we try to make is futile. Once we cross it, our fate is sealed. The only direction is inward. Before we take that final, irreversible step, if you're finding this journey into the unknown as fascinating as we are, consider subscribing and turning on notifications. We explore the universe's deepest mysteries every week, and we'd be honored to have you aboard for future voyages. The ship's thrusters are silent. We have made our choice. The star field in front of us is a swirling vortex of lensed light. The darkness ahead is absolute. With a deep breath, we drift forward toward the quiet waiting threshold, the event horizon of a black hole. We cross. There is no bang, no flash of light, no physical sensation. The event horizon is as intangible as a shadow. But everything has changed. We are now cut off from the rest of the universe forever. And here, one of the strangest predictions of Einstein's relativity comes to life: time dilation. Time, as it turns out, is not absolute. It is relative to the observer and is affected by gravity. The stronger the gravity, the slower time flows. Let's imagine you are watching our ship from a safe distance. As we approach the event horizon, you would see our ship's clock begin to tick slower and slower relative to yours. Our movements would appear sluggish. A message we send you would be stretched out, its frequency dropping, red shifting into oblivion. As we reach the horizon, from your perspective, our ship would seem to freeze there. Its image would hang there, fainter and redder for an eternity, never quite crossing. A ghostly afterimage imprinted on the edge of spacetime. But for us, on the ship, time feels perfectly normal. Our hearts beat once per second, our clocks tick as they always have. The strangeness is not what we feel, but what we see. Looking back at the universe we left behind, we would witness something extraordinary. Because time for us is now passing much slower than time in the outside universe, we would see the future of the cosmos unfold before our eyes. Stars would whirl through their life cycles in moments. Galaxies would evolve, collide, and merge in a blinding, fast-forwarded spectacle. We might see the entire future history of everything playing out in a cosmic film compressed into our final moments. As we are pulled deeper, the tidal forces begin to intensify. Remember how the pull on the front of our ship was slightly stronger than on the back? That difference now becomes extreme. Imagine you are falling feet first toward the center. The gravity on your feet is now thousands, then millions times stronger than the gravity on your head. This differential pull begins to stretch you. Your body is pulled into a long, thin strand like spaghetti. This process has a horrifyingly whimsical name: spaghettification. It would not be a gentle stretch. It would be the most violent and complete tearing apart imaginable. Every part of our ship, every piece of equipment, every single atom of our bodies is drawn into this process. The ship groans, metal shrieks and tears apart, not from an impact, but from the very fabric of space being pulled differently at different points. The forces are so immense that they would overcome the molecular bonds that hold us together. We would be shredded into a stream of individual atoms, a thin ribbon of matter flowing toward the center. The experience would be brief and brutal. Long before we could process what was happening, we would cease to be a coherent object. We would become a part of the inward flow, a trail of particles on a one-way trip to the end. This is the fate of all matter that falls into a stellar mass black hole. For supermassive black holes, like the one at the center of our galaxy, the story is slightly different. Their event horizons are much larger, and the tidal forces at the edge are gentler. An astronaut could, theoretically, cross the event horizon without being immediately spaghettified, surviving for a short while on their journey toward the center, but their fate would be the same. The descent is inevitable. The singularity awaits. Our stream of atoms, once a starship and its crew, now rushes toward the final destination, the singularity. What is it? The honest answer is, we don't know. According to general relativity, the singularity is a point of zero volume and infinite density. It's a place where the curvature of space-time becomes infinite, and all the known laws of physics, including relativity itself, break down completely. Our science, our mathematics, our very ability to describe reality comes to a halt. It is the end of physics as we know it. What would we see as we approach it? It's impossible to say. Some theories speculate that space-time becomes so chaotically twisted that it resembles a turbulent, crashing foam. Others suggest that the singularity is not a point at all, but perhaps a ring, or something even more complex. This is where science enters the realm of pure speculation, where we need a new theory, a theory of quantum gravity, to make sense of it all. We need a theory that can unite the world of the very large, Einstein's relativity, with the world of the very small, quantum mechanics. We do not have that theory yet. So physicists let their imaginations roam. Could the singularity be a gateway to another universe? A white hole spewing matter out into a different cosmos? Could it be a place where information that falls into the black hole is stored? This is the famous black hole information paradox. If the black hole eventually evaporates via Hawking radiation, what happens to the information about everything that fell inside? Is it destroyed forever, which would violate a key principle of quantum mechanics? Or is it somehow preserved and released? The singularity is a wall, not a physical wall, but a wall in our understanding. It represents the edge of our map of the universe. It is the ultimate, here be dragons. For our atomic stream, it is the end of the journey, a silent, instantaneous absorption into a point of infinite mystery. Even as our journey ends at the singularity, the story of the black hole continues. As Stephen Hawking discovered, they are not eternal prisons. Over immense, almost unimaginable timescales, they leak. Quantum mechanics tells us that empty space is not truly empty. It is a fizzing soup of virtual particles that pop into existence in pairs and then annihilate each other almost instantly. But right at the edge of the event horizon, something strange can happen. A pair of particles, say a particle and its antiparticle, can pop into existence. One might fall into the black hole, while the other escapes. To an outside observer, it looks as though the black hole has just emitted a particle. Because of the conservation of energy, the black hole must pay for this emission. It loses a tiny, tiny fraction of its mass. This slow leak is called Hawking radiation. For a stellar mass black hole, this process is incredibly slow. The temperature of its radiation is a fraction of a degree above absolute zero. It will take longer than the current age of the universe for it to evaporate. But eventually, after trillions upon trillions of years, it will have radiated away all of its mass, disappearing in a final, faint pop of gamma rays. This idea leads to even deeper questions. If a black hole can die, what does that mean for the singularity inside it? And what about those other exotic concepts? A white hole is the theoretical opposite of a black hole. It is a region of space-time from which matter and light can only escape, but never enter. Mathematically, it's a valid solution to Einstein's equations, but we have never observed one
and we don't know how one could form. A wormhole, or an Einstein-Rosen bridge, is a speculative shortcut through spacetime, potentially connecting two distant points in our universe, or even connecting our universe to another. While mathematically possible, they are thought to be incredibly unstable and would likely collapse instantly if anything tried to pass through them. These ideas remain on the very edge of theoretical physics. They are fascinating possibilities, echoes in the void that hint at a universe far stranger and more complex than we can yet comprehend.
Our journey is over. We have traveled from the first inklings of an idea in Einstein's mind across the silent boundary of the event horizon, through the horror of spaghettification and into the ultimate mystery of the singularity. The black hole teaches us a profound lesson. It is a place of endings, the end of a star's life, the end of a journey for light and matter, the end of time as we know it, and the end of our current understanding of physics. But in that ending, there is a powerful beginning. The black hole represents the frontier of human knowledge. It is a cosmic question mark hanging in the darkness, challenging us to look deeper, to think harder, and to unify our theories of the universe. It forces us to confront the fact that we do not have all the answers. And now we turn the question over to you. What do you think lies at the heart of a singularity? Is it an endpoint, a new beginning, or something our minds can't even grasp? Share your most creative theories in the comments below. We'd love to read them. And perhaps that is its greatest gift. The universe is not just what we know, it is what we do not know. The black hole is a stark, beautiful reminder that we are still explorers in a vast and mysterious cosmos, and that the greatest discoveries still lie ahead, waiting for us in the dark.